In this video on our series on the Laplace transform, we're going to investigate how we can compute the Laplace transform of either the derivative of a function or of a definite integral of a function. This is going to be particularly useful for us in the next video when we take to taking the Laplace transform of a differential equation that's going to have a whole bunch of derivatives in it. So let's get started. First, I'm going to look at taking the Laplace transform of derivatives. Let me begin with a function that's very nice. I'm going to assume that my f of t is continuous. I'm going to assume that my f of t is piecewise smooth, which means that it's differentiable at all but a finite number of points. And I'm going to assume that it is exponential order. And what we'd seen in the previous video when we studied the existence of the Laplace transform was that when it was of exponential order, that was when you can guarantee that the Laplace transform existed. Nevertheless, I want to now consider the Laplace transform of the derivative of this function of t. And so if I just naively plug it into the formula, it's the improper integral from 0 to infinity e to the minus st as I always have, but now the integrand gets multiplied by f prime of t. To evaluate this integral, I'm going to use an integration by parts. I'm going to observe that I have a v, which is my negative exponential. And then I have a du, which is going to be my f prime of t dt. Then, applying the integration by parts formula, I write it out as vu minus then the integral of dv times u. So what is that integral going to be? Well, let me look at the beginning portion, the constant term that's evaluated at 0 and at infinity. When I plug in infinity, then I'm going to have a negative exponential times whatever f infinity was. And this is where we use the fact that we have it being of exponential order. Exponential order meant that the function f was smaller than an exponential. And as a result, the negative exponential term dominates, and when you plug in infinity, you're just going to get 0. When you plug in 0, then you're going to get, well, e to the 0, which is just 1 times f of 0. And as a result, what I get is just simply this. I get f of 0 for the first term. As for the integral term, I've written it down here as s f of s. Why is that? Well, you see that there's an s sticking out there, and the two negatives come together and make it positive. And then everything else that remains, that is just the capital F of s, or written a different way, this is just the Laplace transform of f of t. So in other words, the Laplace transform of a derivative is just going to be the Laplace transform of the original function multiplied by s and then adding the constant f of 0. What's particularly nice about this is that we have taken a claim about derivatives and replaced that with just the original function itself, maybe multiplied by a variable and added by a constant, but we've gotten rid of derivatives on the right side of this expression. And that is going to be particularly useful to us when we apply the Laplace transform for a differential equation and try to convert it to an algebraic one. So that was the first derivative. I now want to try the second derivative. Let's imagine I've got some function g of t that is equal to just the derivative of f. And then if I'm interested in computing the Laplace transform now of the second derivative, well, what do I do here? This is nothing but the Laplace transform just of g prime by my definition of g. And the reason I've done this and introduced this g is because we know how to take the Laplace transform of a single derivative. We just did that. And so plugging in that formula, it was g of 0 plus s times the Laplace transform of g. So I've used g to apply my previous formula, but now I'm no longer interested in it. So I'm going to rewrite it back in terms of f. So g is the same thing as f prime. So I'll rewrite this as f prime of 0, and then s times the Laplace transform of f prime of t. All right, but again, we can go back and we know how the Laplace transform applies on a single derivative. So I know how it applies on the f prime. So what do I get? Well, the f prime of 0 doesn't go anywhere, the s doesn't go anywhere, but inside I have another f0 plus an s times the Laplace transform of f. So I get this complicated expression, and I can perhaps clean it up in its more standard form as I've got an s squared term, an s term, and a constant term. So for the second time, we've seen how taking the Laplace transform of either a first or a second derivative transforms it into an expression that doesn't have any derivatives in it. Here I'm thinking of f of 0 and f prime of 0 just being just two constants that in general you'll get from the initial conditions. As an exercise, I will leave to you the project of figuring out how could you take the Laplace transform of 3, 4, or generally n derivatives. Can you write down an expression for that? So that was derivatives, and now I want to go the other way around and talk about definite intervals. So I want to compute, for example, the Laplace transform of the integral from 0 up to t of f of tau d tau. Integrals of these form are sometimes called accumulation functions. It is a function of t that I am applying my Laplace transform to, and the t appears as one of the limits of integration. Then you're integrating out some function. Tau here is just a dummy variable. Then I'm going to assert that this is actually equal to f of s divided out by s, and the proof of this claim follows from the fundamental theorem of calculus combined with the methods that we saw before for the Laplace transform of a derivative. Nevertheless, we have this claim. One of the things I want to talk about, however, is if I have the Laplace transform of this integral is equal to this expression f of s over s, I can also go the other way around. Namely, I can talk about that inverse Laplace transform. We haven't talked about the inverse Laplace transform very much, but nevertheless, we spoke in the very first video that it does exist, and really all we do is just alternate the order. And so the inverse transform of the right-hand side just became the inside of the left-hand side. Now, I in particular want to use this to try to talk about how I can do inverse Laplace transforms if I'm given some algebraic expression. Consider, for example, the following. I want to compute the inverse Laplace transform of 1 over s minus a. Okay, some expression. Now, trying to identify it with the structure of f of s divided by s, I'll just sort of rewrite this as a 1 over s pulled out to the side, and then the 1 over s minus a, which is going to be our f of s. Then the claim that we just saw was that this is going to be the same thing as, well, this integral from 0 up to t of the inverse Laplace transform. Now I'm getting rid of the s because if you recall it was f of s divided by s, so the inverse Laplace transform just of the f of s, and the inverse Laplace transform of f of s is just going to be f of t. And then the inverse Laplace transform of f of s is just going to be f of, well, the dummy variable tau. Okay, so now the question becomes, what is the inverse Laplace transform of 1 over s minus a? And this is one that you either recognize or you don't. In fact, we did this in the first video. We had a function whose Laplace transform was precisely 1 over s minus a. It was the exponential. So this is the same thing as the integral from 0 up to t of e to the a tau d tau. That's an integral I can compute, and so I get 1 over a e to the at minus 1 when I evaluate that particular integral. So this is just starting to scratch the surface of the methods to be able to find the inverse Laplace transform of some particular function.